Hello everyone, this is Josh Blade and I worked with Sam Bassett. We did our report on contact resistance. In most cases, contact resistance is negligible. Usually, two solids that are in contact with each other are treated as if the contact was perfect, or in some cases the important heat transfer happens between a fluid and a solid, as with a heat exchanger. However, as you can see, contact resistance is important in computers. The CPU often generates a lot more heat than can be transferred away from it without the use of a heat sink. The contact resistance between the underside of the heatsink and the CPU is significant. Neglecting it can have serious consequences on the lifetime of a computer. When two solid surfaces are in contact, although they may appear to be touching, there are microscopic spaces where they do not touch. Heat must be transferred through the small amount of surface in contact and through these pockets of air or other interfacial fluid. There exist many different methods of dealing with this, including mating the surfaces at high pressure, smoothing out the surfaces, or using some interfacial fluid with a higher thermal conductivity than air. The goal of our experiment was to explore the use of interfacial fluids. Specifically, we wanted to develop an equation that could describe the relationship between the contact resistance and the thermal conductivity of the interfacial fluid being used. We used a few interfacial fluids, which we knew the contact resistance and thermal conductivity for, to establish this relationship. We could then create an equation that would allow us to extrapolate the contact resistance of possible interfacial fluids as long as we knew their thermal conductivity. For our experiment, we placed two identical aluminum blocks, one on top of the other, on a hot plate with a consistent temperature. We insulated the sides of the aluminum blocks, but not the top, and allowed the system to reach steady state so our heat flux would be consistent as energy traveled from the plate through the aluminum. 3 thermocouple probes were strategically placed to measure the temperature of the bottom block right before the interfacial fluid and the top block right after the interfacial fluid. The third probe was placed on the top surface of the top block to measure the change in temperature. We set the heat flux through the interfacial fluid, or T1 minus T2 over contact resistance, equal to the heat flux through the top aluminum block, or Fourier's law, to derive the equation shown. Using this equation and our data, we were able to anchor our experiment to the theoretical values we expected. Multiple fluids with known thermal conductivities were selected to be used in the experiment. They are air, acetone, corn syrup, which was substituted for glycerin, engine oil, water, silicone oil, machine oil, high vacuum grease, and thermal grease. The insulation housing, as seen on the right, was used to simplify the equation used to calculate the contact resistance. Without it, our heat flux would not be consistent between the interfacial fluid and the top block. It was made from pieces of styrofoam that were cut to fit around the 2 aluminum pieces as shown. Rubber bands were used to press the insulation onto the aluminum while also holding the housing together. Aluminum plates were used in our experiment because the contact resistance values listed in the heat transfer textbook were measured using aluminum surfaces. We compared our experimental data with known values for air, silicone oil, and glycerin. These values were calculated for aluminum with a surface roughness of 10 micrometers. However, we did not have the proper equipment to measure the surface roughness of our parts. As seen on the graph, this discrepancy in our experiment had a profound effect on the contact resistance value of air, but was less serious in our silicone oil and glycerin contact resistance values. We used a power curve trendline to generate the equation we would use to predict the contact resistances. We chose to use a power curve because out of all the trendline options, it statistically fitted our data the best. The purpose of our experiment was to predict the contact resistance of fluids based on their thermal conductivity. Therefore, using the equation from the power curve fit, we predicted the contact resistances of machine oil, engine oil, acetone, high vacuum grease, and water. It clearly shows that there is an inverse relationship between the contact resistance and the thermal conductivity. We then tested the machine oil, engine oil, acetone, high vacuum grease, and water to see if our predictions were correct. As seen in the figure, our predicted values for the contact resistances were much higher than the measured values. There was an average error of 62.3%. Some of the inaccuracies in our experiment can be attributed to the physical limitations associated with our project of choice. These include our inability to test the surface roughness of our parts, the difficulty in measuring and maintaining the same interfacial surface area over every experiment, the interfacial fluid running off or evaporating, not being able to fully clean each fluid out of the microscopic gaps in the aluminum, inaccuracies and impreciseness of the thermocouples, contact resistance between the thermocouple probes and the aluminum surface, and perhaps other issues we did not realize existed. However, our data does prove the qualitative knowledge that contact resistance goes down when thermal conductivity in the interfacial fluid goes up. We believed that by knowing the thermal conductivity of any fluid, the contact resistance could be predicted, thus allowing for quick estimates without the need for extensive testing.